Tomorrow's. Okay, no, so here, let's look at compound machines. I want to just do an example. This is kind of a Dr. Seuss compound machine a little bit here.
What's that guy doing?
He's pedaling a bike.
Oh, I see it.
See, he's pedaling a stationary bike, and it's the stationary bike here is hooked up to I'll let you guys kind of see if you can figure out what this does.
So it's like string.
Oh, man,
Is
that's so
in
complex.
plane? It's like pulling out.
Yes.
And then it's attached to a pulley, but like the rope is directly on it. My plane says the plane rises at an angle, it pulls on that pulley, and eventually it pulls 100 kilograms.
Okay, everybody see that? So there's a line that's attached to the wheel that when you pedal forward, it's gonna wrap this line around the wheel. So it's going to provide a tension in this cable that pulls that cable up. Everybody agree?
Mhm.
Okay. That cable is attached to the end of a lever whose fulcrum is down here, right? Also attached at the middle of that lever is another line that wraps around a fixed pulley that travels up and over these fixed pulleys to this pulley system right here, which lifts a mass. Okay, so my simple question is, what is the theoretical mechanical advantage of the entire Dr. Seuss machine, compound machine? What do you think? How are we going to approach this?
Wait, so the first line has that weird angle right there? That first bend?
The first, so here's the first line. First line is right, you need where
It's on the bicycle wheel. Where does it?
Yeah, so it attaches right there.
Yes. And then it randomly pivots right there?
No, pivot point's right there. Right? So it's able to do this. It's attached to the far end. And then it just spools up onto, say it spools up to there.
When it rotates, what happens?
When this rotates,
Yes.
when this rotates, it's gonna get pulled upward, right?
But what does that line connect to? I don't understand.
It connects to the end of the, it's like it's a lever that's pivots about this point. So when he pulls up on it, it's gonna go like that. See what I'm saying? Now let's make the assumption here, for the sake of argument, that this is horizontal to start with, and it's going through relatively small angles. Okay? So in other words, let's just assume that the tension is pointing essentially perpendicular to the lever. We're not going to have to get too, we don't need to go into the arcane details of this. Okay? So, what do you think?
What's the question?
I want to know what the theoretical mechanical advantage of the whole contraption is.
Is it 7.5?
On that.
Say it again?
I just can't quite tell what's happening. I don't know if everyone else can.
So here's the first part.
What's the first pull unit?
So Nick's pedaling on this wheel, and then when he pedals on the wheel, it's going to wrap this
Yeah.
line up,
I
which is
know,
going to
it's
pull
pulling
the
it up.
line up in that direction,
But
right?
what is the first pulley doing? in
So,
relation
okay,
to
so the
stick?
first pulley. So here's the second line. So the second line attaches right there. It loops down around that pulley, and so when he pulls up on this thing, what's that going to do to
Pulls
this
up.
line right here?
Pulls up.
It's going to pull it up there, which means it's going to pull this part down, right? Because this pulley changes direction,
Yeah.
right? So then this line right here is going down. Well, that line is connected,
Yeah, I see now.
so
I
now
just
this
didn't
thing is
understand-
moving up, right?
I just didn't understand what those first lines were doing. How it was pulled. I just didn't see the.
Okay. Yeah, see, these are just there to give you some dimensions. So suggestions, how we could go about calculating the theoretical mechanical advantage of everything. So you were going to say something.
I had an answer.
Oh, I don't want an answer. I just want to know how could you go about it?
You could just pick each part, like with the pulleys, find the advantage of that, and then find the advantage of, say, the wheel, then the advantage of the lever, and then combine them.
Okay, so let's do that. So let's take each individual simple machine and let's calculate a theoretical mechanical advantage. So what are we gonna get, Richard, for the block and tackle here, for the pulley system?
Yeah, 5.
5, good, because we have 1, 2, 3, 4, 5 lines supporting the load, right? So we'll call that, for the third machine in this sequence, we've got a theoretical mechanical advantage of positive 5, okay? What about Walter, what about the lever down here? Okay, now, think in terms of, everybody real quick, let's remind ourselves, what is the just for any lever system, theoretical mechanical advantage is equal to what? No, not that hard. You don't need to worry about it. But for any machine, theoretical mechanical advantage is always, what? Input, not force, input distance. So d sub I over d sub O, right? And for a lever, the input distance is gonna be what? Where you're applying the force. Look at this,
Input
so
is
here's the
gonna be forward.
fulcrum.
Input is forward.
Does that make sense? Because that's gonna be the input arm is the distance from where you're applying the force, right? The input force to the fulcrum, right? So we're gonna get 4 over, what's the output distance, the output arm? Does that make sense? Well, that'd be 2 then, yeah, so it'd be distance from where the machine is working on the load, right, to the fulcrum. So we get TMA sub 2 equals 2, 4 over 2. And then what's the other simple machine we're acting here? Wheel, yeah, right, we end up with a wheel and axle here, right? So what's the input distance on that one? Okay, so, well, but what's the input distance?
15.
So that's gonna be 15, right? Because you're applying the force at the axle, or the wheel that you're pushing on, in other words, has a radius of 15 centimeters, right? Does that make sense? So you're pushing that far from the axle, right, from the pivot point. So 15 centimeters divided by the output radius is what? 20. Right, so in this case, this is kind of a backwards wheel and axle, right? Technically, this time, the axle is always what the line that's lifting the load is wrapped around. So the axle is bigger than the wheel this time. It's fine, you can do that, right? So what is TMA? So 1, simplify 2 then?
3/4.
Good, 3/4 or 0.75. So that one gives us a mechanical disadvantage, which is consistent with a regular bike, isn't it? Right, regular bike, you've got an excess of force that you're trading for for extra distance or speed on a bike, right? Okay, so then how are we gonna link all these together?
Multiply.
Multiply, yeah. You just multiply. The theoretical mechanical advantage for a compound machine is just a product of all the theoretical mechanical advantages of the simple machines that build it, right? So we're gonna get 3/4 times 2 would be 3/2. 3/2 times 5 would be what? 3/2 times 5 would be, say it again? 7.5. 15 halves or 7.5. Okay, so what's that tell us then? Theoretically, if I want to move this thing up 1 meter, how far am I going to have to?
7.5.
I'm going to have to move my feet through a circular distance of 7.5 meters, right? But what's the weight of this thing? No, it's not a weight. Times 9.8, so say roughly times 10. So this is about 1,000 newtons. Okay, so roughly then, how much force am I gonna have to apply to the pedals to pick this thing up, theoretically speaking?
It's just a question back, so you
Yep.
have to go 7.5 meters. Lift it 1 meter.
1 meter, right. I'd have to move, and when we say 7.5 meters, in this case, what's that mean? Well, we're gonna have to move our feet through 7.5 meters of circle, right? The tangential distance I'm moving is 7.5 meters. What's the force I'm gonna have to apply theoretically to pick up this 100 Newton mass?
Me 1,000 Newton. Yes.
I mean 1,000 Newton, sorry.
133.
So I'm just gonna divide by 7.5. So I only have to apply 133 newtons.
133
Pick this thing
and
up.
a third.
103, right. And in reality, is that gonna be accurate? No, for sure it's not. Absolutely for sure it's not. Even if there was no friction in here, why am I for sure gonna have to apply more than that?
Because that's just equal.
Well, that would be equal. But even if there's no friction, what about this system? Something we talked about the other
Oh,
day.
with the lever.
No, not the lever. Because the lever, if it's all perfectly friction-free, the lever should be, there should be no frictional losses there. Yeah, what about the pulleys? I gotta lift the weight of the block, right? It's the movable pulley that's sitting on the mast. And that can't weigh nothing. So no matter what, even if this is a highly, really expensive, ultra-low friction device, that's still gonna be pie in the sky, still not gonna be able to get it. In reality, no chance. All these pulleys are gonna have friction, right? So, make sense? Okay, how would I determine the actual mechanical advantage?
Input force.
Yeah. Divided by output force. You have to measure the forces. You have to measure the force you're applying to the pedals. That's the input force. And the output force is easy to calculate. What's that?
It's just the
1,000 newtons, right? So you'd have to take the ratio of output force to input force to actually calculate what the actual mechanical advantage is. Okay? All right. I think you got everything you need. Why don't you, sounds like this is kind of a joyous week for people in Bio 2. What are the other tests? AP US history. Okay. So I'll let you work today on wrapping up that second circle machines second. And I'll go ahead and put, just so we don't test this week, I'll add one more small part to this. We'll talk about torque tomorrow. I don't think so. I mean, but I'm not gonna even, because Ben, I totally trust Ben. Ben knows what he's doing.
So you
Ben's
know,
got
our-
it. Yeah.
You better have us fast forward. He will.
There's no question in my mind.
Yeah, but besides, but if I wanted to move it from there, I would have to rotate, I would have to rotate this. Isn't it?
You're smart enough to do it, Walter.
I did it.
You solved it all on your own. Good
I
job.
finally got the entire thing working, so now theoretically they can pick up a ball, and over like 5 minutes, we can put it into a basket. You've got it, you get it's like that long, it's got a massive crane and an arm right there. And then there's a bunch of variables from holding up.